Hello everyone, welcome back. In this video presentation, we're gonna talk about test benches in VHDL. Um, if you did in your garage on a workbench any debugging and testing, or if your parents, grandparents did anything like that, where you would have some electronic circuit and then you would apply input stimuli to the circuit, the design under test, you would look with the scope to observe the outputs and troubleshoot and debug. That was the idea of troubleshooting and testing let's say electric product. The idea of doing that is basically what test benches in VHDL are trying to do. You define a test bench just like you would have a workbench in your garage, and use the design entity as a design under test, also known as circuit under test, unit under test, doesn't matter, to which you would apply certain inputs, stimuli, let the design under test produce its outputs, observe them, and compare them to what you would expect that those outputs should be. And if for any of the input stimuli your observed output is not what you expected, then testing fails. So that is basically the idea. So test benches are really useful during the debugging development of our design entities, and we use them to verify that the functionality, the behavior of our design entities is what we intended through our architecture descriptions. And a test bench, we'll see shortly examples, is declared just like a regular design entity. The difference is that it doesn't have any ports to the outside wall. Just like if you think back in the backbone of that workbench in the garage, you had on the workbench everything: the function generator, signal generator, the design under test, your scope. Nothing came in and nothing went out that particular workbench. Similarly, in the case of a test bench, everything is self-contained and everything is happening inside it on the test bench. An important thing to remember about test benches is that they don't need to be synthesizable. Test benches are useful, and their role purpose is really to be used with simulation tools during the development stage of a project. Another interesting thing to mention about test benches is that they implement what is referred in the world of testing and design for testability as the principle of testing, which is graphically illustrated in this slide here, where we have a design under test that we want to test to see if it's good or not. And in the principle of testing, we would apply test vectors, input test vectors, or input patterns, one after another. This is a digital circuit, but this generally applies to any other type of product, hardware, or even software that you want to apply. And test. So we would apply this input test vectors one after another. We would collect the output responses and compare them to the expected responses that are typically stored. And if for at least one of the input test vectors, the output is not what we expect it to be, then that design under test fails and has to be removed. You don't want to ship that to your customer. So basically, test benches in VHDL try to implement this principle of testing. They help us detect whether our design entities, as we have them described in VHDL, implemented that functionality behavior that we meant it to be. This is the general structure of a test bench. As I said, it is declared just like an entity, and in this case called my underscore TB is, and it doesn't have any input and output ports, as I said before. And it has to have an architecture description as well, which will see more details about in the examples later on. The best way to introduce the different types of approaches of writing test benches is to look at a couple of examples. And the first example is a combinational circuit, the 4-bit adder. The test bench declaration is shown over here, called test bench underscore 4-bit underscore adder, and that test bench is just like any other entity declaration without any input and output ports. The architecture description includes in this first part the declarations of the component which we will instantiate as our design under test using port mapping, and a couple of local signals that will use to connect that instance to our a test bench to provide inputs and observe outputs. This statement here only specifies what particular architecture we want to use for that particular 4-bit adder design entity in cases where that design entity might have different architecture descriptions, because that's possible. While the design entity declaration is unique for any given design entity, as you may remember, we may describe multiple different architectures. So when you want to simulate that design entity, you have to specify which architecture you want to use to be simulated. And then here inside the main architecture body between begin and end, we have a process inside which you have as many testing cases as you may want to add. In this case, I have just two cases. In the case one, I want to apply to inputs A and B all zeros, and assert whether the output will be all zeros. This is my expected output, and the carry output as well, with a couple of delays introduced here of 10 nanoseconds. By the way, the nanoseconds doesn't have any bearing with reality. It's just an arbitrary time unit to have the waveforms show some separation among these cases that we are looking at and simulate. They are not also statements that are synthesizable, and that's one of the reasons for which this type of design entity is not synthesizable. But that's a different story. Let's get back here. So I just want to input as input stimuli A and B, and observe that the expected outputs are this and that. And if by any chance that design under test will not produce these expected outputs, these assert statements will stop the simulation and will indicate, will tell me, will notify me or exactly at what step of the simulation that failed. In the second case, I'm inputting wall once, and I'm expecting this output and this carry output. That is pretty much it. Here we look at the simulation of that test bench, which I have already created as a project and run the simulation. As you can see here in the waveform viewer, we have exactly those two cases that I tested for on the input A and B or 0, 0, the output Z that the design and other test produced are all zeros, and the carry output 0, while for the second case, the inputs were all ones, and the output produced were as shown in this waveform viewer. So the designer under test produced the correct output, so the simulation was successful. If let's say I wanted to do some more cases, I could let's say add an additional case here. I could have it as case, let's say 3, and add I don't know, let's add a all ones and B0001. In that case, that would be the output will be should be a all zeros, and the carry output should be a one, because 1 plus 1 is 0. We carry 1, and then that 1 and then 1, and the 0 is 0 again. We carry 1, and so on and so forth, and we'll have a carry output at the end. So this is what I expect the output to be. So let's save this, and compile again this modified files, and then simulate, start simulation of that test bench 4-bit adder. Now I added an extra case there that added an additional 50 nanoseconds. So I'll put here that the run length of the simulation should be 150 nanoseconds to capture that as well. And then I will add the signals to add wave to be able to see them after the simulation is done, run, and full zoom full here. And as you can see here, the third case, let's actually change this to radix binary. And as you can see here, when we added in the third case all ones with 0001, the output generated by the designer under test is all zeros, and the carry output is also on. So that case passed as well. So the second example of a test bench is for a sequential circuit for our edge detect design entity, which is declared right here as a component, which we'll want to test. This will be our designer under test. The test bench is again an entity without any input-output ports called edge detect test bench. The component declaration is right here, and a couple of local signals: clock underscore I, reset underscore I, level underscore I, tick underscore O. This is one aspect of my own coding style of adding this underscore I for saying that's going to be a local signal that is going to be used as an input for the input stimuli, and underscore O for outputs. It's going to just make looking and browsing through the waveforms that I'm going to look at a little bit easier, but it's not that relevant. And then within the begin and end of this, we have two processes in addition to the port mapping that instantiates that design under test inside this test bench. One that will always be like so. Here is the process that we use always to generate a clock signal that our sequential circuits will need. So it's best to generate that with a separate process that we call clock underscore generation. We assign to clock 1 and wait for an arbitrary 50 nanoseconds, and then set it to 0 and wait for another 50 nanoseconds to get a 50% duty cycle clock signal with a clock period of 100 nanoseconds. And then the second process shown on the right hand side here is the one where we'll assign different levels, one or zeros, to our as input stimuli to our design under test. Use and play with this wait statements as shown over here to test meaningfully based on how we know that this edge detect circuit works, different inputs, and then observe the outputs. So this is again a sequence, a series of assignments of values to input stimuli, and then using the waveform viewer will investigate and look at the outputs produced by this design under test. So let's do that. For that, I wanted to actually also show how one would create a project within the simulator. So it's always good. So I have the files right here. I have them added inside a folder that I called edge underscore detect underscore TB, and I have placed the VHDL files inside that in preparation for creating this project. So I'm gonna go and open the Intel Questa simulator, which is our simulation tool. This is the old model sim for those who remembers them. And I don't need this. Close this project. That was the 4-bit adder test bench. I'm gonna create a new uh, project. Come on. I'm gonna call it edge underscore detect underscore TB, which was the name of the design entity as a test bench from that VHDL file. For historical reasons, it's a good practice to always call the project name, the folder name, and the top level test bench design entity name using the same. I don't think it's absolutely necessary anymore, but that's for historical reasons. So I select that folder. This is the project name. The default library name stays that work. Say okay. Let's add existing source files to the project because I had them placed already in this edge detect underscore TB local folder that I had created. And that is how you would create the project in Questa. Let's open the test bench. And you see here that uh, edge detect underscore TB design entity with no input and output ports, the edge detect component, local signals, and then the port mapping, the instantiation of the design entity, and the two processes, one that generates the clock and the other one that creates all of those signal assignments to inputs, which will make for this design under test to produce some outputs that we'll see with the waveform viewer. After the project compiles successfully, we should start the simulation by saying start simulation and going and selecting that edge detect test bench, or you could switch here from project to library and select this edge detect test bench and say simulate. And then that opens up this simulation dialog window. It shows the signals that we want to add to our waveform viewer to see after we run the simulation. And let's run up to, let's say, 1500 nanoseconds, a little bit longer than what we actually need. Hit this icon, run, and then say full zoom and maybe undock this to be able to see it maybe a little bit larger here, and full zoom as well. So as you can see here, if you remember the edge detection circuit, by the way, we could have had assert statements throughout this process of setting different input values and waiting for different times, just like we had for the 4-bit adder. Just didn't do it here. I'm relying all on looking at the waveforms to decide and see whether this operates correctly or not. So If you remember, anytime for the edge detection circuit, anytime when the level input changes from 0 to 1, the output tick generates a short pulse to indicate the detection of that rising edge. At the beginning, the reset signal is set to logic 1 for 2 clock periods, and then is being set to 0 up to the end of the simulation. This is the point, the moment, the time when the simulation restarts. So ignore that part. I had it here a little bit longer than needed to just show that the simulation restarts if you set a simulation time longer than all your wait statements inside the test bench. But otherwise, as you can see here, for different lengths of this input, um, level I signal being logic 1, the rising edge of it is always detected, and the output tick is generated correctly. The insight or the observation here to note is that for this implementation of this edge detection circuit, which was our melee implementation, the duration of the output pulse depends on the timing of arrival of that rising edge on the input level. And I have here a couple of different situations where the output tickets still generated correctly, but of different lengths as observed using this waveforms. That is pretty much it about this edge detection circuit test bench. Going back to my presentation here, long story short, remember for both combinational and sequential circuits, it is really easy to create and describe these test benches. They are really helpful, useful at debugging our design under test. And a test bench is nothing but a design entity, a special one in the sense that doesn't have any input and output ports, and we use them to verify the behavior, the functionality to be the intended, the correct one. So do not underestimate the value and the importance of test benches. They can be really handy at discovering early on bugs that later on could be much harder and much more time consuming to troubleshoot and debug once you deploy your projects onto the FPGA hardware. That's pretty much it, and I'll see you.